that?
Computer audio? Wait. I can't hear anything. Oh, there's me.
Now, gentlemen, you're not going on electronics yet. At 11 o'clock, Lori will be in class. At 11 o'clock, I will be listening to the... Hi, I'm talking to you. Hi. To the Indiana governor. And when you can do your... We have 2 days we've said we were going to read them. We haven't done that yet. We have to.
Okay, good morning, everyone. Can you hear me well? Can you guys hear me well?
Yeah, I can hear you.
Okay. All right, so this is not the way it should go, but unfortunately, that's the way we have to go. So my idea is I will try to run this class online the same way I ran my class regular. Are you with me? So we start by ask me questions. I go through the homework with you, so you guys know exactly how to solve the problems. And after that, I will go through the lecture. Now the lecture is already on Blackboard. I hope you guys have it. I'll walk you through it. I cannot write it all over again. It just takes forever with us. We're gonna just work with it slowly, slowly. Are you with me?
Yep.
Okay, I would like some reply. You can use chat to tell me that you guys are with me. All right, so as we start the class, usually I would like to go through some of the problems that I've assigned last time. All right, you guys, did you do homework as usual?
Yes.
Okay, I want more than, write on chat if you guys don't want to speak in person. Just chat and tell me which problem did you have trouble with so we can go through them. Anybody would like to tell me the problem that they had trouble with? Put it on chat. You know, today is very much experimental, so we get going. Use chat to write which problems you had trouble with. Nobody? All right. So I will go through some of the problems from the previous section. I will pick some by myself and I will do them. And tomorrow, I hope you guys will come with very specific questions. Are you with me? Okay. I would like some of you just to talk or to say something that I make sure that I'm talking to someone. It's hard to talk to myself when I don't see your faces.
Okay.
All right?
Okay.
I need to see, otherwise I don't know who I'm talking to, which is hard, very hard. I don't like this.
I
I'm
know.
going to it. So I planning to go last time when we left. We were working with sequences and we defined what a sequence is. So remember, a sequence was nothing but a list, an infinite list of numbers, no more, no less. So we will go through some of the problems I've assigned. And today I will pick, as I said, tomorrow I want you to pitch in more. So I'm gonna pick, for example, number 15. So I will write it up and we will see how to do it. So number 15 are giving me the following sequence. -3, 2, -4 third, and 8, 9, and -16 over 27. Dot, dot, dot. And the question is very clear. Find a formula for the general term an. So here they gave me the term and it's our job to find a formula. So does anybody have an idea? So we need to find a sub n. What's the formula of a sub n? It means what's the formula of the general term? So how we do those type of problems? We start watching a pattern. Is there any pattern coming up? So if we watch the pattern here, that's a 4 over 3, 8 over 9, 16 over 27. So the pattern seems to be 4, 8, 16, which should remind us what? 2 square, 2 to the power 3, 2 to the power 4, right? And down here I have 3, 9, which is like a 3 square, 27, 3 to the power 3. And it's alternating, minus, plus. So in class last time, we know that alternating its contribution is -1 to the n, that we may have to fix the n later on. And then how does it look like? It looks like it's a 2 to the n plus 1. That's how the pattern seems to be, over 3, and the power of 3 is one less than the power of 2. So this is going to be 3 to the n. So that's my first attempt. Are you with me?
Yes.
Anybody beside Lori is with me?
I'm with you.
Okay. So now let us check. For which value of n is this working? I will try it. So if n is 0, what are we picking up? If n is 0, I'm picking up 2 over 3. So I'm picking up this term for n equals 0. If n equal to 1, what am I picking up? Minus 2 squared, it means -4 over 3. So I'm picking up this term. So the only term that I'm not picking up is -3. So let us see if we can get it at -1. So if I put n equal -1, what do I get? -1 to the -1, which is a minus, and then 2 to the power. What I'm getting here? Yeah, 2 to the power 0, which is 1, over 3 to the -1, which is basically 3. So that's going to be the general term of the series. Is that clear? From Christian to me. Yes. Anybody else? All right. Any questions about that? You can, if you want to ask a question, unmute yourself and ask the questions. Is that clear? If you have a question, unmute and ask it. All right. So now we're going to move to 2 other problems. So you guys, all those pattern problems, that's really how we proceed. I would like to do 2 other problems before I proceed. So one is simple problem, number 25. Okay, they gave us the general term, a sub n, and it's n to the power 4 over n to the 3 minus 2n. And they tell us what happened when n becomes very large, what happened to the terms of the sequence. So when n takes a value 10, 100, what's really happening? Are those terms getting close to something fixed, or they are really going to infinity? So we need to compute the limit as n tends to infinity of a sub n. It means the limit as n tends to infinity of this term. So how we can compute the limit? Now we analyze it. When n becomes very large, the numerator becomes very large, and the denominator is becoming very large. So we can go 2 ways. Either we can use L'Hopital's rule, or we can, as we did, all of us did in 163, divide by n with the highest power. We can pick the n with the highest power in the denominator or in the numerator. So we're going to divide by n to the power 3. This will help me out. So it's going to give me the limit as n tends to infinity of n to the 4 over n to the 3 divided by n to the 3 minus 2n to the 3 to the 3. Now, if we simplify a little bit, this is going to give me n in the numerator. Denominator, I will have 1 minus 2 over n as n goes to infinity. Okay, so what will happen now? As n goes to infinity, my numerator goes to infinity. 2 over n goes to 0. So I will have infinity over 1, which is infinity. It means that the sequence an diverges, because diverges mean either the limit does not exist. So like we did in class, the limit can get, some terms become close to one number, some others become close to another number, or the limit goes to infinity. That means also diverges. All right? Is that clear? No answers.
Yeah, that's clear.
Yes.
Yes, I want answers. I don't see you. Remember, I I rely a lot on your faces when I am teaching you in class to see what's going on. I don't have your faces now. All right, I will do, my plan was to do one more problem. I will do number 33. Now, before number 33, if we go to this problem here, did we expect the limit to be infinity? Did we expect that actually? I mean, intuitively, the numerator is n to the 4. The denominator, intuitively, that's at the intuitive basis. When n becomes very large, n to the 2n is very negligible compared to n3. So its values we can almost think that the denominator almost equal to n3. So this is almost equal to n. So n goes to infinity, it means this whole thing is going to become very, very large. So even I want you to do the whole work to show me equal infinity, but intuitively we expected that because this is almost like n to the power 4 over n to the power 3 because 2n is negligible compared to n to the power 3. All right, now we're going to move on to number 33. One of your classmates did ask me about this problem on Blackboard, so we will go through that. So number 33 was the following. So we have an equal n squared over the square root of n to the power 3 plus 4n. And now, what are we supposed to do in this scenario to find the limit? And the question is, we want the limit as n tends to infinity of n squared over that. Now, it's not as easy as the scenario as the previous one. It's very clear. So the scenario is a little bit harder. So the question is, what am I supposed to do in this case to compute the limit? Any idea? So how can I do to actually do with that? All right. I'm letting you think a little bit. You need to move, yeah. Christian, is the paper moved up well?
Yeah, it's moved up well.
Yeah, okay. How do you think we're gonna do this problem? Anybody can answer?
Rewrite it, maybe? Rewrite the denominator?
How?
Like that be in parentheses to the power 1/2?
We can do that. What will this improve? What will this help us to do? That's a correct operation, but will it improve the problem? So what's bothering us here? There is a square root down in the denominator, but there is no square root in the numerator, correct?
Mm-hmm.
So what are we gonna do?
Put the whole thing under the square root by squaring the top.
Exactly. So we're gonna try to do it so the whole thing became under the square root. But how can we do that? And square, we're gonna rewrite it as the square root of n4. Is this mathematically correct?
Yes.
And what's the benefit of this is going to be? The benefit of this operation is going to be that I will be able to put the whole thing under the square root. So with that, I can rewrite this as the limit. As n tends to infinity of the whole thing under the square root. Now, if I can do that, and then I can proceed as in the previous problem to find the limit of the term under the square root. So now I can exactly repeat verbatim what I did before. So this is gonna be, I divide by n4 inside. And this is gonna be 1 in the numerator, 1 plus 4 over n in the, n in the numerator, divide by n3. N in the numerator, and then 1 plus 4 over n in the denominator. Now when n goes to infinity, these terms go to 0, the upper term goes to infinity, the whole thing go to infinity, the sequence diverges. Okay, so that's the trick we play in this problem just to make things a little bit easier for us. All right. One more problem I would like to do. And if you don't have any suggestions, I'm going to pick a problem by myself. And I hope tomorrow you will have, you can email me your suggestions, or you can put the suggestions on the discussion board so we can all learn from them. The other problem I'm going to look at is number 35. And my sequence here is a sub n equal -1 to the n over 2 square root of n. So here it is alternating. You know, the sequence does alternate, minus, plus, minus, plus. But what's the limit? Anybody?
0.
0. Is Lori correct? Is it 0? And let's see why she's correct. I'm going to write this way, -1 over this term. Okay, and let us explain what's happening here. I'll explain it on the number line. So my term are -1 to the n, 1 over 2 to root n. Watch what's going on. When n becomes large, when n is large, 1 over 2 root n become close to 0. Correct? Because root n goes to infinity, 1 over infinity become close to 0. Now what's the behavior of the an? The behavior of the an is, let us take n equal to 1. I will have
All right.
-1 over 2.
Our governor does not talk as much as the other ones. Okay.
Please, I have to mute every student. I don't want to hear any noise in the background. Is that clear?
Okay, listen to me first. Lori is in class. So, but
Lori,
if I hear
mute.
screaming
Lori,
up
please
there,
mute.
you will
Okay.
Okay.
not be on there anymore.
All right. So, 1 over 2 here. If I take n equal to 2, so if I take n equal to 1, I will have -1 over 2. So this is -1 over 2. N equal to 2, I have 1 over 2 root 2. If I take n equal 100, I will have 1 over 2 square root of 100, which is getting close to 0. N equal 101, I am right here. So that's a 100, but still closing to 0. So because this term, 1 over 2 root n, goes to 0, the -1 over n is not going to affect. The terms are going to go to 0 from both sides. So the limit here is equal to 0. Okay? So before I proceed to the new material, I want to contrast this with the one we did on the board in class. So let me contrast this with the following. -1 to the n times n over, let us say, to n plus 1. What's happening to the limit in this case? Does the limit exist in this scenario? What can you say?
No, it doesn't.
Okay, what's happening here? I usually like to watch those terms. That's really how I go about it. I watch the term n over to n plus 1. When n goes to infinity, if you divide by n, numerator, denominator, this is equal to 1/2. So those terms without the -1 to the n become close to 1/2. When I put -1 to the n, how the picture will be affected? The picture will be affected like that. If n is even, so -1 to the n become 1, positive 1, then I will have positive 1 n over to n plus 1. So all the an, where n even, become close to 1/2. However, all the an, where n odd, become close to -1/2. So conclusion, the sequence diverges.
Wait, so I'm kind of confused. How do you get 1/2?
If you compute the limit of n over to n plus 1, as n goes to infinity by itself. Are you with me?
Mm-hmm.
What's the limit of that? Divide by n, numerator and denominator. What do you get? N over n.
Infinity over infinity?
Yes, correct. It's infinity over infinity. Then you can easily use L'Hopital's rule, or you divide by n, numerator, denominator. You get 2n over n plus 1 over n.
Oh, you divided by the highest power. Okay.
Right. Now, what I will have in the numerator left? 1. What's in the denominator? 2 plus 1 over n. When n goes to infinity, 1 over n goes to 0, and I will be left with a half.
Okay.
All right? Okay, that's how we do it. Or you can use L'Hopital's rule. So talking about L'Hopital's rule, one more, and I will definitely be done. So let me take 41. So number 41, I have a sub n equal to n squared times e to the minus n. And the question is, what happens as n goes to infinity? Analyze it. When n goes to infinity, n squared goes to infinity. What about e to the minus n? What happened to e to the minus n when n goes to infinity?
Goes to 0?
Absolutely. So that's e minus n is 1 over e to the n, correct? When n becomes very large, e to the n becomes very large. 1 over something large is very small. So I have infinity times 0. I have a large number times a small number. This is indeterminate. A large times a small, could be large. So one way to play around with that to find the limit is to rewrite it. Instead of having e to the minus n here, I'm just going to write this as an equal n squared over e to the n. Now, what's the benefit of doing this? What's the benefit? My goal is to compute the limit as n tends to infinity of n squared over e to the n. What do you think the answer is going to be? Do we know the answer? I will do the work, but I want you to know what the answer should be. Which one goes to infinity way, way, way faster? N squared or e to the n? We've talked about that in class. E to the n goes to infinity way faster than n squared. Means we expect this to be equal to 0. But now let us do the math. So that's really our answer should be. Now, infinity over infinity, that's indeterminate. And this is a scenario where we cannot divide by n squared. This is where we can use L'Hopital's rule. So it's the limit of derivative of the numerator over the derivative of the denominator. So which is going to be equal to the limit of. Now, again, when n goes to infinity, my numerator goes to infinity, my denominator goes to infinity. I'm going to use L'Hopital's rule again, and I will get 2 over en. Now, as n goes to infinity, 2 over something very small is equal to 0. So the limit of n squared, so my sequence converge, and it is equal to 0. All right? Okay, so today I took over. Tomorrow I really expect you to give me specific questions, so I would rather work with your questions. All right, now we're gonna go back to the new material. I still had one thing to talk about it for sequence, and then we will move to our new idea series. So as you guys know, you have the lecture in front of you, but the note about the sequence is the following. We're gonna look at the sequences that have the following format. So suppose I look at the following sequence. A half square, a half cube, a half to the power 4, those type of sequences. Okay, so another type of sequence, 1/3, 1/3 squared, 1/3 to the power 3, etc. This type of sequence we're looking at. So we're looking at a sequence of the following form. R squared, R cubed, R to the power 3, R to the power 4, R to the power n. This type of sequence, it's like a half squared, half to the power 3, half to the power 4, and so on and so forth. And the question is, when does the sequence converge? For which ratio R, for which R they converge, and for which R they diverge? So what's happening is the following. Suppose, before I give you the rule, suppose I'm looking at the limit as n tends to infinity of 2 to the n. So here my R is equal to 2. So when n becomes large, what happened to do to 2 to the n? So I'm looking at 2 squared, 2 cubed, 2 4, and so on and so forth. So what is going to be the limit in this case? Absolutely infinity, correct? Now, what if I take the limit? Now, graphically, if I think of the function 2 to the x, that's the function 2 to the x. As x goes to infinity, 2 to the x actually goes also to infinity. So at 1, that's a 2. 2 squared, 2 cubed, 2 4, and so on and so forth. So it really goes to infinity. Now, what if I take the limit as n tends to infinity of 1/2 to the power n? What's going to be the limit of that? So what is 2/2 to the power n? If we think about it, it's a half. So for n equal 1, it's a half. N equal to 2 is a half square. It's 1/4. N equal to 3, half cube. It's 1/8. What's happening here that every time I'm multiplying by a half. That's a 1/4. Every time I multiply by a half. So what I am doing actually is I'm making the term every time smaller and smaller because I am multiplying it by a half. Every time I make it smaller, I multiply it by a half. I multiply it by a half. So what's going to happen in this case? So the limit of that is going to be the limit as n tends to infinity, 1/2 to the n, which is going to be actually equal to 0. Graphically, we remember the exponential function. The function f of x equal a to the x. When a is less than 1, the function totally decreases and head towards 0. So if I take a to be a half, so if I draw a equal 1/2, what's happening? The function is decreasing, 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 is really heading towards 0. So this limit is going to be equal to 0. So what is the general rule? Suppose we have a sequence of the form r squared, r cubed, and so on. If r in absolute value is less than 1, then the sequence Rn will go to 0. So if the ratio less than 1, think about a half squared, a half cube, the terms are getting less and less and less because 1/2 is less than 1. If the ratio is bigger than 1, then the sequence will diverge. So I'm going to look at the following two limits. The question is, find the limit as n tends to infinity of 0.1 to the power 8. What's the limit? So what sequence I'm looking at? I'm looking at the following sequence. 0.8. 0.8 square. 0.8 to the power 3. That's the sequence I'm looking at. 0.8 to the power 4. And the question is, what happened to those terms when n becomes large? So this has the form r squared, r cubed, r4, where r is less than 1. It means r is 0.8. Since it's less than 1, the limit is equal to 0. Now let's take another problem. The limit of 2 to the n over 3 to the n. When n becomes large, what happened to this limit? The numerator go to infinity, the denominator go to infinity. You can use L'Hopital's rule. Try it by yourself. You will realize you're going to be in a vicious circle. It means L'Hopital rules, you will never get out of it. Try it. So I'm going to rewrite it in the following format. I rewrote it as 2/3 the whole thing to the power n. Now, what's the benefit of doing this? By writing it this way, it's become the following sequence for me. It means it's become the sequence 2/3 to the power 2, 2/3 the whole thing raised to the power 3, 2/3 the whole thing raised to the power 4, and so on and so forth. So now I can find its limit. So it has exactly this format. R is less than 1, it means this is equal to 0. Okay, my last example for that is limit of 1.01 to the power n. So here, definitely, this is my R, 1.01. And my R is bigger than 1. So the question is, what's the limit? In this case, when my R is bigger than 1, the term keeps getting larger and larger and larger. Okay? All right. So the terms get larger and larger and larger. It means the limit is equal to infinity. All right, so there's very specific type of sequences that come up with us, and it's very important to know how they behave. All right, any questions?
Nope.
Nope. All right, so now we're gonna move to the idea of infinite series, okay? And that's the new material, infinite series. First, what's a sequence? I repeat, a sequence is just an infinite list of numbers, no more, no less. You have a sequence of numbers, a list, that's what a sequence is. Now, suppose we have an infinite, we're gonna define the idea of a series the following way. We start with a sequence, an, and we add the terms of an. So we get a1 plus a2 plus a3 plus a4 plus dot, dot, dot. This is called an infinite series. And using the sigma notation, we denoted sigma n equal 1 to infinity of an. So I can write something like 1 plus a half plus squared plus 1 to the power 3 plus dot, dot, dot. So here the an, the terms of are 1 over 2 to the n. But the question is, what does it mean to add infinite many terms? It's really, so what does it mean to add infinitely many terms? I'm gonna motivate by basically an example. So I'm gonna consider the following series. Sigma 1 over 2 to the n. It's a half plus 1 over 2 square, 1 over 2 cube, 1 over 2 4 plus so on. And what does it mean to add them? What we're going to start doing is add the sum of the first 2 terms. Then we're going to add the sum of the first 3 terms, the sum of the first 4 terms, 5 terms, 50 terms, and see what happens when I start adding more and more terms. So what we will look at the following sequence of finite sum, because infinite sum make no sense. Absolutely no sense. So what we're gonna look at is the sequence of finite sum. What do I mean by that? So this is what we mean. So the first term is a half. So let me see. Yeah, the first term is a half. Then I'm gonna take the sum of the first 2 terms. So what's the sum of the first 2 terms? It's a half plus 1 over 2 squared. If I add those, I will get 3/4. All right? If you don't trust me, do it yourself. Now, what's the sum of the first 3 terms? So I'm going to add the first 3 terms. It's a half plus 1 over 2 squared plus 1 over 2 to the power 3. 7 over 8. So the idea, I'm going to start adding the terms slowly, slowly. Every time I'm going to add 1 extra term. S4, I'm going to add 1 extra term, 1 over 2 to the 4. So it's a half plus this plus 1 over 2 to the 4. We do the math, I get 15 over 16. Okay? S5, I'm going to do the same thing. A half plus 1 over 2 square plus 1 over 2 cube plus 1 over 2. So I add an extra term, 1 over 2, 5. I do the math, I get 31 over 32. Now, a certain pattern emerges. And we can actually definitely see the pattern. It's not a hard pattern. We're not going to prove it, but we're going to at least see it. So 7 over 8, 15 over 16, 31 over 32. So the numerator is always 1 less than the denominator. Now, what is the denominator? Let us watch. 8 was nothing more than 2 to the 3. 16, 2 to the 4. 32 is 2 to the 5. So the pattern seems to be that if I add the first 5 terms, I'm getting the denominator is 2 to the 5. The numerator is 1 less, 2 to the 5 minus 1. We actually can prove this, but I don't want to worry about the proof now. I just want to worry about the idea of a series. So what I'm doing so far, I computed the sum of the first 2. Then I added 1 more. I added the 4th. I compute the sum. I took the 5th. I compute the sum. So the pattern tells me that if I take the first 100 terms and physically add them to each other, just add them, simple multiplication. This is a finite sum, I can add them. I'm getting 2 to the power 100 minus 1 over 2 to the 100. So if you're patient enough and you pick up your calculator and you add those 100 terms, you're gonna get that much. But if you look at this term very closely, this term is very close to 1 because you have 2 to the power 100 minus 1 over 2 to the power 100. This is really, really close to 1. And the pattern continue. What do I mean the pattern continue? It means if I'm going to add the first 1,000 term, I'm going to get 2 to the power 1,000 minus 1 over 2 to the power 1,000, which is also almost equal to 1. So if I add more terms, if I add the first 1,000 terms, 2,000 terms, I'm getting a number very, very close to 1. So that's what I'm saying here. We noted that as we add more and more terms, those sums that we're going to call them partial sums become closer and closer to 1. So it's very reasonable to write that the sum of the series is equal to 1. That's really the idea of an infinite series. We cannot add infinitely many terms. Forget it. That's not the way it is. We start adding terms. We add the first 2 terms. Then we add, so what we're doing is we're adding those 2 terms. Then we're adding those 3. Then we keep adding and adding and adding. And ask ourselves, are we getting close to something? If we are getting close to a number, it means my series converge. And if we don't get close to a number, we will say that my series diverge. So let's go back and define. Definitions, I'm going to repeat this with the formal definition. Definitions of partial sums and conversions. So what are partial sums? We start with an infinite series. It means something like that, A1 plus A2 plus A3. And we associate the following. So now this is the definition of the partial sum. We associate the following sequence. S1 is the first term. S2, the sum of the first 2 terms, like I did in the previous example. S3, the sum of the first 3 terms. S4, the sum of the first n terms. Sn, the sum of the first n terms. So to every series, we're going to associate the following sequence. Sn. Sn is called the sequence of partial sums. So when you have this infinite series, this bunch of stuff, what we do is we start taking the sequence of partial sums. And then if those partial sums converge to a limit s, like what happened in the previous problem, that is, if the limit of Sn equal to S, then we say that the series sigma An converge, and we write A1 plus A2 plus A3 equal to S, or the sum equal to S. So saying that sigma equal to S means that those sums, the sequence of partial sums, are getting close to S. If the sequence Sn diverge, we say that the series diverge. Okay, so what does it mean for a series to converge? I'm going to pull up the paper. A series converge if the sequence of partial sums converge. Means if we start adding the terms and adding them, we get close to a fixed number. So when we write, when I write or you write, when we write sigma an equal S, we mean by that by adding sufficiently many terms of the series, we get closer and closer to S. That's what it means. So when we write this equal to S, it means when we start adding more and more and more terms, we get the value S. So what does it mean infinite sum? It doesn't make sense. We're giving it a meaning. We're telling you what an infinite sum means is the following. You take the partial sums. And if those partial sums become close to a number, we say my series converge. So let's take, we don't have at this stage a lot to work with. So I'm going to take a simple series. Let me consider the following series, sigma n equal 1 to infinity of n. First, what does this mean? What am I talking about? Okay, it means I'm adding stuff. What am I adding? If n is 1, is 1. Plus, if n is 2, 2. Plus, if n is 3, 3. Plus 4, plus 5, plus 6, plus 7, plus 8, plus. That's really what I am adding. 1 plus 2 plus 3 plus 4 till infinity. Now, does the series converge or diverge? All right. Intuitively, of course, it diverges. But before we do that, let us compute the partial sums, just to get practice with that. What is S1? S1 is the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms. So it's 1 plus 2 plus 3, which is 6. S4, 1 plus 2 plus 3 plus 4, which is 10. S5, 1 plus 2 plus 3 plus 4 plus 5 equal to 50. And you keep going. So does the series converge or diverge? It means those sums, are they going to get close to anything or they're going to blow up, basically, in this simple problem? What do you think? Blow up, absolutely. Anybody agree with Christian?
Yeah.
Yeah, as you add more term, if you think about S6, it means you're adding 6 to 15. Right? If you think about S100, it means you're taking 1 plus 2 plus 3 plus 4. So S100 is bigger than 100. S101 is bigger than 101. S1000 is bigger than 1000. S1,000,000 is bigger than 1,000,000. So it means, of course, here that as we add more and more term, Sn will go to infinity. So the series diverges. Okay, so this is a simple problem because that's how we have so far. Now, this is another example. Okay, another weird example. Does the series sigma n equal 1 to infinity of -1 to the n converge or diverge? Okay, since we have, I'll give you 3 minutes to find the partial sums in front of you. Okay, each one of you find the partial sums. That means I want you to find S1. Okay, I'll write on another piece. You do it. Don't just do it. Okay, I'll do it with you. You guys do it. So it is sigma. Okay. All right. Okay, what did you guys get for S1?
Be -1.
What?
-1.
-1 is she correct? Because if I start writing this as a sum n equal to 1, that's -1. N equal to 2, plus minus 1 square plus minus 1 to the power 3. That's what this is. Minus 1 to the power 4, minus 1 to the power 5, etc. That's really what this read. All right, that's what this notation means. So S1 is minus 1. What is S2?
Positive one?
What?
Positive one?
Positive
Zero.
1? No. 0.
Negative one.
What? No, watch. S1 is this term. What's S2?
Oh, you
Sum.
add them both. Okay.
You add them both. So it's minus 1 plus minus 1 square. Is that clear? What's that? 3? You add. Be careful. Partial sum, you adding the term. That's not the minus 1 plus 1. That's not what the partial sum. Partial sum, you adding those terms. So what is S3? Okay,
-1.
so it's minus 1 plus minus 1
-1.
square plus minus 1 to the power 3. Are you with me? How much is gonna give me?
-1.
Negative 1. Now S4. Again, plus, I'm doing this so you guys get the feeling of what I am doing. I'm just adding stuff. And we know that those already it's minus 1 because this is the same as before. And then I'm adding 1 to it. This is equal to 0. Those are the partial sums. They have nothing to do with the term of the series. So those are not the minus 1 to the end. Those are the sums we're adding. We add those. We add those. So let us see S5. Okay, so it's the same as S4. So it's the same as this, but I'm going to add one more term to that. And this is going to give me minus 1. So what's the sequence of partial sum in this scenario? So the sequence of partial sum. So this is the partial sums. The partial sums are the following sequence: 0, minus 1, 0, minus 1, 0, minus 1, etc., etc. That's the partial sum. That's the sequence of partial sum. Does this sequence converge? Does this sequence converge?
No.
No, because what does it mean for a sequence to converge? A sequence to converge, it means all the terms has to get close to one number. Those, they don't get close to some number. Some of them are stuck at zeros, some of them are stuck at minus 1. So when n is large, we cannot find something, a fixed number that they all become close to. Now they are 0, minus 1, 0, minus 1. They don't get close to a fixed number. So in this case, the limit as n tends to infinity, you guys tell me what, of Sn do not exist. We don't have a limit. It's just totally blow up. It means my series diverges. Totally diverge because it doesn't get close to any fixed number at all. Okay, so what does it mean for a series to converge? A series converge if the partial sum means, that's really the key idea. It's the sum, those sums, as you keep adding term, ask yourself, do we get close to something? If we get close to something, this is going to be, the series will converge. So suppose I write to you the following sentence. Very bizarre, nothing hard. I tell you that sigma 1 over 3 to the n equal 1 to infinity. It means a third, that's what the sequence 3 to the power 3 plus 1 over 3 to the 4 plus dot, dot, dot. I tell you, this is equal to a half. What am I talking about? What am I telling you? What info I am conveying to you when I tell you that this sum is equal to a half.
That it converges to 1/2?
But what converges to 1/2? I'm going to be picky about that.
The partial sums.
The partial sums converge to 1/2. That's what it means. It means if I start adding those terms, the sum become close to 1/2. That's really what it means. So if I compute 1/3, now I don't know if I'm going to try something, see if it works. Okay, tell me if it works. I'm going to try to share the screen with something. I'm not sure it works. So I'm going to try to see if I can get it. No, I'll practice that. I just want to show you, actually, I added those. So this means that if I take those, actually, if we compute those numbers, take a calculator and compute them, I actually computed them. I compute the sum up to 1/3 to the 100. I got 0.49999. That's what I got. That's really what it means, equal 1/2. It means those sums become close to 1/2. It means if I add more and more terms, I get closer and closer to 1/2. Okay? Any questions? All right, how did it go, guys? I want you to tell me what went right, what didn't go right, so I can fix it. Are you with me? Were you able to follow everything I said?
Yes.
Yeah.
Okay, so if you guys have any remark, please write them, and I will appreciate it. Okay, so that's it for today. For tomorrow, your homework will be on Blackboard. Right now, I will put it once I leave you guys. Your homework will be on Blackboard. I expect you to do the following: to do the homework for tomorrow, and I opened a discussion board. I don't know how well it's going to work. Okay, I opened a discussion board. You can put on the discussion board the problems you had trouble with, and this will help me. So when I start, I know exactly what you guys are struggling. And we will do exactly what I did today. I'm going to put the lecture on Blackboard right now and in a few minutes. And the best of luck. Okay? Stay safe and wash your hands.
So just to confirm, you're going to be putting up the recording?
I recorded it. I will try. It's
Okay.
all new to me, to be honest. So my son is helping me with all this stuff. I'm not good at it. So I'm going to try to see if I can put the recording, because I did ask it to record the lecture. So
Okay.
hopefully I can put that. Any other questions? Any other question? Now, you know that I know the attendance because I have everybody is right there. So those who don't attend, I know exactly who they are. I expect you to attend. You have nothing else to do anyway. We're all stuck at home. So, okay. Any other questions?
Will you
Alright.
be still having our quiz on Friday, like usual?
Yes. My plan for now, and I don't know how well it works. My plan is to put the quiz on Blackboard like around 10:30 on Fridays. And I'm going to give you a time limit, like 45 minutes at most, and you guys take it. So that's what will happen this Friday. And I will see what I come up. So if I end up with student cheating, I will find some other ways to deal with you. Is that very clear? I don't want you to cheat. It won't get you anywhere. You are at home. You can do anything you want. I cannot actually do anything about it. So try to be honest in taking the quiz. You know that I know you very well. So try to be honest in taking the quiz. So on Friday, I will put the quiz on Blackboard. And what I expect you to do, to take the quiz and then make a, download it into Blackboard. And I will grade it. I will have a practice quiz before that. So like probably on Thursday, I will give you something. I will open it for you and I tell you just write your name on a piece of paper and download it. So I make sure that each one of you know what to do. And Friday, it will be the serious one. All right, so you will have a quiz on Friday. I will try to hold everything the way I do it in class. That's what I'm gonna try to do. That's my goal. All right? Any
Okay.
other questions? Okay. All right, I'll give you homework so you guys don't get bored. Okay, bye guys.
Thanks.
Sure, bye-bye.